So we have also implied that to meet the global warming targets, we need to be at negative emissions by 2050 or net zero by 2050 as a whole, and various countries have declared their net zero goals. As you know, Sweden I think is at 2035 or maybe 2045, US at 2050, China at 2060, India at 2060, and negative emission technologies are constantly mentioned. So what are the physical and economic limitations to negative emissions that we hope for? So this paper looks briefly at that in terms of the biophysical and economic limitations. So we know already that fossil fuels are taking out geological carbon and putting it into the system through the atmosphere and then into land and ocean. Bioenergy wants to take up some of that CO2 and replace the geological source with the captured carbon, but then it wants to put it back at some time scale. Carbon capture and storage, on the other hand, would take fossil fuel CO2 that is being created back into the geological storage, whereas bioenergy plus CCS or BECCS is going to take it out of the atmosphere, fix it in the biosphere, and then sequester it away with carbon capture and sequestration similar to here. So there is a net reduction here, whereas this is going to leave the current levels there by just substituting fossil fuel emissions, whereas direct air capture is going to take what is in the atmosphere out and try to put it into the geologic storage. As we have talked about several times, none of the technology that exist right now are scaling up anytime soon. So let's hope some game changer comes along and really cranks this up. Enhanced weathering is of course grinding up rocks and throwing them on the soil with co-benefits for soil carbon, soil nutrients, soil moisture, crop yields, and so on, and maybe even extending to reducing land use for agricultural production because of this enhanced crop yields. So it's going to take carbon out of the atmosphere and with reactions with minerals is going to put it into geologic storage. Afforestation and changed agricultural practices will try to take it out of the atmosphere, put it into land, which has a different time scale of putting away carbon than the geologic sources. Ocean fertilization and alkalinization, enhanced alkalinity experiments are basically about taking CO2 out of the atmosphere and putting it into the ocean, and again hoping that those time scales are also long enough. If long enough is kind of a very qualitative term, because even if it's 100,000 years, it becomes a intergenerational ethical problem, right? How many generations are end up going to face this issue, or who's going to be saddled with this emission problem even before birth, and so on. So scenarios including negative emission technologies for each of the scenario categories corresponding to the ranges and median values shown in that table that I'm not going to show here. Basically, it's using the IPCC scenarios for the future for various global warming targets shown in gray here. So business as usual would take us into net emissions in that range with concentrations over 1000 ppm CO2 equivalent, and the global warming targets would want us to come back down below negative by 2050, reach net zero by 2050, and then go negative as we said before. So in the context of historical emissions, couple of integrated assessment models are used here to compare the different negative emission technologies to crank down the emissions at various times with various rates, and the idea is to see what are the biophysical and economic limitations to these negative emission technologies that are being assumed to exist to accomplish these kind of drawdowns. Okay, so negative emission technologies are basically going to take out more carbon than they emit, right? So it's not just zero, it's actually negative. So here the different requirements and impacts of negative emission technologies are looked at in terms of negative emission technologies that have different land requirements, water requirements, nutrient requirements, and different geophysical impacts on climate here, and generate or require different amounts of energy, and entail different capital and operating costs. So this is kind of a summary diagram. So let's just look at this first. What is being shown? Area required in hectares per year per ton of CO2. You have crop-based bioenergy and carbon capture and sequestration. So crop residuals, dedicated crops for BECCS, and dedicated crops on marginal lands. And CDR is carbon dioxide removal with direct air capture, for example from animals, and enhanced weathering with grinding up olivines and so on. And forest BECCS include boreal forests, pine forests, coppices, and tropical forests. So this is land. In terms of water required thousands of meter cube per ton of CO2. So this CO2 ton of carbon equivalent, sorry, not CO2 but carbon equivalent. So you can just see, relatively speaking, crop residues, dedicated crops, and dedicated crops on marginal lands with carbon capture and sequestration here requiring some water as well. So that's from the feedstocks, and here again is direct air capture and enhanced weathering. And forest BECCS again require various levels of waters based on whether they are boreal, pine, coppice, or tropical. Okay, here is the nutrient requirements. So nitrogen concentration in I can't even leach block divided by biomass, sorry, feedstock. I read it, and then when I look at the caption, I'm forgetting it. So nitrogen concentration in feedstock divided by the biomass, so kilograms nitrogen per ton of carbon equivalent for the same choice of BECCS, crop BECCS and forest BECCS. Okay, so am I missing anything? No, it's okay. So here is the change in so biophysical impacts. You can look at various things. This is looking at albedos. So change in albedo is negative, means you're going to trap more CO2 in, or you're going to warm, you're going to trap more of the solar energy because reflectivity is reduced, so you're going to trap more energy, so you're compensating for the carbon that's taken out by reducing albedo. So here is the positive albedo band, and none of them are in it. So various crop BECCS and various forest BECCS and boreal forests with snow have tremendous change in albedo, very high change in albedo. Why is that? Because the forest BECCS are requiring more water and land, and there is various future scenarios involved as well in running the integrated assessment models. Okay, so let me make sure I have everything. Sorry, I have to pause here. I have to attend to something. Sorry, I live in this place where a lot of things keep happening. So Okay, so we have been looking at forest BECCS, bioenergy and carbon capture and sequestration, along with afforestation and reforestation included here. So when you do that, you can have boreal forests where the trees come way above the snow line, above the snow cover, and they are much less reflective than snow for sure. So they end up basically being a massive impact both in boreal forests, and boreal winter and summer albedo changes. So you can imagine that this is not good news in terms of how much emissions are going to be reduced by BECCS versus how much warming is going to happen because of reduced emissions, because in general forests are much less reflective than crops, for example. So the change in albedo from crops is not as severe as change in albedo from forest cover. Okay, so looking at net energy in gigajoules per ton of carbon equivalent here, you have some that require, so crop BECCS here, energy is produced, so this is for crop BECCS, but some of the dedicated crops can have energy requirements, and dedicated crops on marginal lands will also have energy requirements, and you can see that there is hardly any net gain in terms of energy here. So you have to just focus on other impacts in terms of whether net carbon is taken out. Direct air capture and enhanced weathering will both require energy, whereas the forest BECCS on the other hand have energy that's going to be produced. So you have to compare the enhanced warming versus energy produced that is going to substitute for emissions from the fossil fuel energy that's going to be displaced as a net negative emission technology here. So the cost of mitigative emissions in US dollars per ton of carbon equivalent, you have to see what baseline is used, but nonetheless you can see that there is cost and there are savings. So you can see that the crop BECCS is down here, so you can if you can see that afforestation and reforestation have been removed from here in these estimates. So below here you have again DAC and enhanced weathering costing up here in terms of negative emissions in costs in US dollar per gigaton carbon equivalent, whereas forests again have costs down here. So the scale is changed here from 50, so this is 50, 100, 100, 100, and then you jump to so you can see the various costs. So eventually global impacts of nets for the average needed global carbon removal per year in 2100 in a 2 degrees C consistent scenario, which will leave us at 430 to 480 ppm in the scenario category. So you can map it onto RCP 2.6 for example. So the negative emission technology is BECCS, DAC, enhanced weathering and afforestation and reforestation, with some details here that I'm not going to go into. Global carbon removal in gigaton carbon equivalent per year in 2100. These are the numbers: 3.3, 3.3, 0.2, and 1.1. So these are mean and maximum being shown here from the integrated assessment model estimates. The mean land requirement in millions of hectares in 2100, 380 to 700. For DAC it's going to be very low unless solar PV is used for energy. So you want DAC needs energy, and if you use renewable energy, land requirement may go up because you need solar panels. So you always have these kind of trade-offs. For enhanced weathering and afforestation, you can see afforestation mean and maximum are quite a range. Estimated energy requirements here again, BECCS is net negative, DAC has positive. enhanced weathering has 46, so lower than these, and afforestation and reforestation require very low energy, as we already saw. Mean water requirement, just reiterating what we saw before, various ranges. For BECCS it's quite high, for DAC it's lower but still has a range, especially considering it needs energy as well. And for enhanced weathering, there is the range from mean to maximum, and for afforestation and reforestation, of course, water requirement is going to be high. So there is a lot of debate about afforestation and reforestation are actually that good negative emission technology, because unless they are protected against wildfires and so on, they can actually end up becoming or at least belching out all the carbon that has been sequestered. And in terms of land use, what they displace, whether it's agriculture and what it means for food security and what this means for water security and so on, are always key issues. So there are a lot of caveats involved. Nutrient impacts in kilotons nitrogen per year in 2100 can be variable. DAC doesn't affect those, neither does enhanced weathering, whereas afforestation and reforestation have a mean and maximum range that's quite large there, right? Albedo impact, BECCS is variable, as we saw. DAC doesn't influence it, and enhanced weathering is not expected to influence it. Afforestation and reforestation can be negative, or reduced greenhouse gas benefit where not negative. So if it's negative albedo impact, which it'll reduce reflectivity and lead to warming, or it can reduce greenhouse gas when albedo is enhanced. So investment needs for BECCS for electricity biofuel in US dollars per year in 2050, 138 billion, and the minimum is estimated to be 123 billion. So you can see that that range is quite large. DAC is expected to be much greater than BECCS. Enhanced weathering, so relative to BECCS, is greater than BECCS, and afforestation and reforestation are much less than BECCS. Again, remembering the caveats of land requirement and water requirement. So obviously negative emission technologies have biophysical and economic limitations. Looking at it here, negative emissions in gigaton CO carbon equivalent per year, energy produced versus energy required, and land requirement. The impacts and investment requirements of negative emission technologies to meet the 2°C target by 2100 with 66% probability. A schematic representation of the aggregate impacts of nets on land, energy and water, and relative investment needs for the levels of implementation equivalent to BECCS. So everything is compared against the baseline of BECCS, which is at 3.3 gigaton carbon per year negative emissions in 2100, as we saw here. In scenarios consistent with a 2°C target or mean and maximum attainable where that level of negative emissions cannot be reached. Water requirement is shown as water droplets with quantities in cubic kilometers per year. All values are for the year 2100 except relative costs, which are for 2050. Okay, so negative emissions, BECCS appear, energy produced, and in terms of land use, it's somewhere here. Water used, it's here. Afforestation, reforestation has a range, as we already saw, with high land requirement or relatively low land requirement and various levels of water requirement. DAC is up here in terms of energy required and water required. Enhanced weathering is down here with very little land needed and very little water needed, but also not great in terms of negative emissions of gigaton CO2 carbon equivalent per year. Okay, so keep this in mind, that when we rely on negative emission technologies for the future, we must worry about all the caveats of biophysical limitations and economic investments needed. So the return on investments and the goals accomplished have to be considered as a total. These are of course results from integrated assessment models, so they have many assumptions that go into them, so one has to be careful as well. But as we saw, they often provide a range of outcomes, so one has to treat these as what if scenarios and not deterministic answers. Okay.